Okay, now let's talk about PDEs, which is partial differential equations. You've already took a course on differential equations, so you've seen differential equations before. The definition of a differential equation is simple. It's just an equation that has derivatives in it, right? So what's the definition of a partial differential equation? Yeah, equation with partial derivatives in it. There are some important partial differential equations that they carry a name. So let me give you a few examples. So one is ut equals to k times uxx, where k is some constant. This is called the He equation. I will explain what this equation means later in the course. Okay? Another important equation is, oh by the way, this notation ut means it's a partial derivative of this function uxt. U is a function of x and t, and you're differentiating u by t. That's what it means. Okay? So this would mean that you're differentiating u with respect to x twice. That's what it means. Is that okay? So another equation is utt equals to c squared uxx, and this one's called the wave equation. And there's something called the Laplace equation, uxx equals uyy equal to 0. These are like the simplest non-trivial differential equations you can think of, because these are second order. You can also do first order, but it's not that hard. The second order is where it starts getting serious. And then these coefficients, there's this constant. So it's like you can think of uxx plus uyy as 1 times uxx plus 1 times uyy. So this is, again, a constant coefficient linear differential equation. I say linear because none of the u's are squared. Okay? If you have u multiplied with any of its derivatives, or if it's squared, then you call that nonlinear. Nonlinear equations are notoriously hard. In most cases, you don't even know if your approximate solution would do anything. Okay? So let me give you an example of a nonlinear differential equation, which is pretty famous. This is a vector equation. So here, u is a scalar function. It's a function from multiple variables to a single number. You feed in x and t into u, you get a single number. Okay? On the other hand, for this equation, u gives you a vector if you feed in t, x, y, z. Okay? So it's a function on the space x, y, z with respect to time. And if you differentiate u by t, it satisfies that the gradient of u dotted with u minus the gradient of something called the pressure, and then plus mu u with respect to, and there's an additional one because there's a separate function p having a single differential equation wouldn't be able to give you both. And you also need the second one, which is divergence of u is equal to 0. So this equation here is called incompressible Navier-Stokes equation. And the thing about this is that we don't even know if you provide this equation with some initial conditions, you can have a solution. Do you have a question?
Is that one of those 7 problems that...
Yes, that is correct. It's a Clay question. You know, the 7 questions of Clay Institute, they carry $1 million prize if you are able to solve it. So only one of the 7 problems are currently solved, and this is one of them. So knowing whether this differential equation always has a solution, and if the solution is unique, if you can prove that, then you get $1 million. It's very hard because, see, this derivative of u, the gradient is like u differentiated with respect to x, y, and z, right? And this is a dot product, so it's like component-wise multiplication here. So because it's multiplied, this is a nonlinear differential equation. And though this is still prettier than just some random partial differential equation that's nonlinear, it's still unproven whether this has a solution or not. Okay? All right. So that will be like out of reach for our class. In this class, we will mostly deal with these 3 types of differential equations. And I will also talk about their meaning later on. But then, I also want you to know that, see, in the eyes of a mathematician, it doesn't matter whether you're using t or y, right? So you might as well write this equation as uyy equals to c squared uxx, and it's pretty much the same thing, right? And in general, if you have a constant coefficient second order differential equation, then they will, and then let's say the 2 variables are, let's say that u is a function of 2 variables only, then the most generic constant coefficient differential equation, partial differential equation you can write down will be something like this. It will be like a times uxx plus b times uxy plus c times uyy. That's all the possible second derivatives, right? Then you can have d times u, you can differentiate u by x, and then you can differentiate u by y, and then you can differentiate, and you can choose to not differentiate at all. And you can, let's say, it's a homogeneous one, so that it's 0. But of course, you can have some other function on the other side. Okay. So that's the constant coefficient one. And if you make a parallel, I mean, we just talked about change of variables, right? You have like other u and v 2 variables. Unfortunately, I'm using u here, but if you change the variables, then you can change how this one looks, right? And that situation is very similar to a quadratic curve quadratic curve in the plane. So these are also called conic curves because as long as at least one of A, B, C is non-zero, then you get either one of the three cases. Do you know what they are? Anyone? It used to be part of college education, but it's dropped out, so you've probably never seen it. But sometimes this could be a parabola. Sometimes this could be an ellipse. Sometimes this could be a hyperbola. Okay, and that depends on whether b squared minus 4ac. This is called the discriminant, right? So if this is 0, this is parabola. Okay. And then b squared minus 4ac is less than, let's try positive. In that case, it's going to give you hyperbola. Then b squared minus 4ac less than 0 gives you ellipse. And all of these mean that, what's a parabola? A parabola is like y equals x squared, right? What's a hyperbola? X squared minus y squared equals to some constant, right? And then what's an ellipse? It's like x squared plus y squared equals to some constant, right? In general, ellipse means that you have some constants here, but that's like this simplified one. So there's a change of variables from here to one of these three things. Well, this could be plus c. One of these three things, depending on the sign of b squared minus 4ac. Okay, provided that at least one of a and b and c are non-zero. Okay, so that's why such a name exists, and mathematicians figured out that similar thing happens here too. So just read this as like y equals to kx squared. So what's that like? If you have the equation y equals to something x squared, what's that? What's the picture?
Parabola.
Parabola. So this one is called a parabolic PDE. And this one is like x squared minus, if you move this to the other side, it's like x squared minus c squared y squared. So this one is called the hyperbolic. And then this is like x squared plus y squared equals to some constant. That's like a circle, right? So it's an ellipse in general. So this is called elliptic PDE. And this generic constant coefficient second order PDE can be also classified depending on this discriminant. Okay? Whether b squared minus 4ac is 0 or positive or negative, you can classify them and they behave similar to this one. Okay? In fact, if you have anything like that, then you can change the variables to make it look like this, except that you might have a plus something times u at the end, plus something times u. But their mathematical behavior is very similar. On the other hand, the solutions of these are very different. So, I mean, I haven't spoken about what initial value problem is, what boundary value problem is, and all that, but it turns out that for Laplace, this one, you can provide boundary values, even if the boundary values are not continuous. The function inside the domain will be not only continuous, but will be infinitely differentiable. So it has a very good regularity. That's what people say. This is some jargon that you can't understand at this point, but later on, if you study PDE more, then you will understand. Okay? The wave equation if you have an initial condition that has some discontinuity or cusp or something like that, then it's going to carry over in the solution. The solutions will have these characteristic lines where that point of discontinuity or cusp will just continue there. Okay? And heat equation is somewhat in between. But they have different behaviors. So that's why parabolic, hyperbolic, elliptic are a very good good way of categorizing PDEs. Okay? And theories that work for elliptic doesn't work for hyperbolic and vice versa. So, yes?
Can you repeat again why those three equations has their name?
Oh, if you just replace the derivatives by like their function, so instead of differentiating by t, just think of it like t equals to x squared, and replace t by y. What's that? That's a parabola, right? Yeah. That's why it's called parabolic PD. And the classification is there because they have some theory behind them that behave very differently. So in fact, you could also think about a second order PDE where A, B, C, D, E are all functions of x and y. And what that could do is like, this could be only true for certain values of x and y. So for some x and y points, you might have this parabolic. Some other points it's hyperbolic. Some other points will be elliptic. If you have a mix of those things, then it's considered a very, very hard problem, even if it's a linear PDE. That's like already, if you have a mix of a hyperbolic one and elliptic, like people had major trouble trying to solve those problems. I heard that when you write down the differential equation for like the air passing through an airplane, you end up something like that, and then it's very tough. And only with recent computer simulations they were able to find some approximate solutions. It's impossible to solve by hand. Okay? Yeah. All right. So you have these classifications, and then there's a very important concept of well-posedness. A PDE is considered as well-posed if it satisfies the three things. Existence. If you know that the solution exists for the problem, that's a good thing, right? Yeah. If you don't know, then when you try to solve it, you're kind of like trying to solve a question where you don't know if the answer exists or not, right? And then number two, uniqueness. So if you don't know if the solution is unique, then let's say you worked out a problem and you solved it. How do you know that that's the only solution? You might have a secondary solution that you never thought of, right? So that's another important thing. And number three, stability. It's like when you have a boundary condition or initial condition of a PDE, the solution will vary only slightly if you change those conditions slightly. Okay? If your solution changes suddenly by a lot, by small change in the boundary or the initial conditions, then that's a bad PDE. But I'm saying it's bad because often you can't solve a PDE, you can only find numerical approximation for them, and your numerical approximation will be highly unstable and not trustworthy if it's not a stable PDE. So that's number three. So you need three things, and proving these three is of the first concern for mathematicians, because once you know these three, then what you can do is you can just solve a PDE, not really solving it, but by just guessing. Okay? So here's something that your ODE professor might have failed to elaborate. See, if you're a keen student, when you took the very first differential equations course, you might have found something, which is that a lot of times they do something and they find the solution, but it's not like step by step. You don't start from the PDE and go over logical steps to get the solution. You just say, oh, for this type, this is the solution. So you work out some formula and that there's the solution. Right? So for example, if you have like a constant coefficient one, a times y double prime plus by prime plus cy, how do you solve this? You just say, oh, the solutions usually look like e to the r1x, e to the r2x, c1 plus c2, right? You just say that. And then how do you get r1 and r2? Those are the solution of the characteristic equation, which is ar squared plus br plus c, right? Now, have you ever questioned why? Yeah?
I saw that. I think the e-x is the only function that can be performed like that. So.
Well, okay, but there's like a big logical step that's missing, where your ODE professor might not have elaborated really. So here's the thing: if you have an ODE, ordinary differential equation, which means that there is no partial derivatives, only just regular derivatives, then if you have a second order ODE, then providing the initial condition y of 0 equals to some value and y some value and y prime of 0 equals to some value will give you a unique solution. That's proven. So you don't learn it, but then you learn it in later harder course in differential equations. It's called Peano's theorem. The Peano's theorem says that if you have an ordinary differential equation, especially if it's constant coefficient, and you're given two initial values, then the solution exists and it's unique. It doesn't talk about stability. Stability is for people who do numerical simulations. Okay, so we know that it exists and it's unique. Okay? So now let's think about what that means. You just do this and you do this and you can show that this satisfies that. Then we're done. Why? Because first of all, this process is legit because I know that the solution exists, so I can just go ahead and guess the solution, right? But then once you show that it solves this one with the initial conditions for C1 and C2, then because of the uniqueness, I found the only solution that exists. It's just like this. In elementary school, when you're taught algebra, your teacher might ask, x plus 3 equals to 5. And then, class, what's the solution? And Johnny sitting in front, he raises his hand and says, it's 2. And the teacher asks, okay, why? And Johnny says, well, I see that 2 plus 3 does give you 5, so 2 must be the answer. And the teacher says, wrong, you can't do that because you're guessing. You're not supposed to guess. You're supposed to subtract 3 both sides, and that's how you get 2. That would be like the logical step, right? But now, Johnny is right when it comes to ODE because you're guessing the solution, right? You plug it in, 2, and it works. And we know that this type of equation can only have one solution. So we found the only solution that exists. That's like a little more convoluted way of thinking, but that's what happens in PDE. So now you kind of see why mathematicians and physicists and engineers, they like to know existence and uniqueness. See, for incompressible Navier-Stokes, people don't know that. And they still do numerical simulations. And because of that, things happen. Like you can go to famous conferences in fluid dynamics. This is for fluid dynamics. And they'll have same exact problem solved by 2 different groups using different numerical methods. And the solutions are different. And you don't know which one's right. Maybe they're both right because we don't know uniqueness. Okay? That's the current state of fluid dynamics. That's the problem that we face. If somebody solves a Clay Institute problem, then we can definitely see something like, if it's unique, then you can say one of the groups made an error, right? If it's not unique, then maybe both groups have the solution, and we don't know which one to choose. Maybe in reality they both are true. Who knows, right? That's the problem. However, lucky for us, we're not doing the nonlinear ones. These are hard. We only do these. Okay? And for these, existence and uniqueness are proved. Even stability is proved. Okay? Now these solutions are very hard. Well, actually, existence, often you just show that some solution works, right? So once we solve it, it's going to work. But uniqueness is, well, I'll try to show uniqueness for one of them. It's called energy method. So we're going to try something. So I guess that to summarize what I'm trying to say here is that we don't solve PDEs. We make good guesses. Okay? The solution sounds more like, oh, let's try this. Oh, that works. Okay, now let's try to change this a little bit so that it works with these other cases as well. Does it work? Yes, it works. Then what does that mean? We found the solution because of the uniqueness. Okay? So that's a very different mentality, and that's why students not knowing this, when they try to learn a PDE course, PDE from a textbook, they have major trouble.